Good morning, good afternoon, good evening, everyone. This is Celso Batalha here, and this is Ch2, and we are going to focusing on subjects of Chapter 2. So, Chapter 2, let me pull up the notes. Just a second. I have them here. Class notes is right there, and I have them right here. So, if you go to Moodle, the publisher of our book made available some slides, and I would like to go over a few of them, not be so aggressive about it in a little bit. So those are important, and quickly, here's what we're gonna be focusing. Basically, the motions that you should be able to perceive on a daily basis, even if you don't have a telescope or if you never care to observe the sky. You should be able to be aware of days and night, right? You should be aware that there is some awesome object up there in the sky, the moon, that goes through phases. Sometimes the moon appears to be full, sometimes the moon appears to be not completely full, um, and its entire circumference is not entirely filled. So, why is that? And you might, when you are asking questions as to why nature behaves the way it does, then you are doing science. At least you started doing science. And that's what we did 3,000, 4,000 years ago when we start asking fundamental questions, attempting to come up with reasonable answers as to why celestial objects they change configuration in the sky and they change their relative position, sometimes in an hourly basis, sometimes in a monthly basis. And if information can pass on through generations and generations and generations, then we might be able, even be able to detect very subtle changes we call precession of equinox. So all of this is pretty much tackled in chapter 2. So let me show you um, a landscape, and the sun is up there in the sky, as you can see. Um, this letter S indicates south, southeast, and southwest. So basically, this is a position from an observer in the northern hemisphere. In fact, this is set to San Jose, United States, December 29. That's when I'm taping um, this lecture. And what I'm going to do is to allow the time to flow, and the time is flowing now. As you can see, look at this, 9:53, 45, 46, 47, 48, 49. So time is flying 1 second every second. And if you look clearly in the sky, you don't see a lot of change, right? In a real situation, you might be able to see the clouds moving because of wind patterns, but apparently the sky doesn't move. But since this is a software, one thing I can do is to speed up the time flow. So the time is not going to flow um, 1 second every second, but several minutes per second. So if we do that, if we speed up the time flow, see what happens. The sun goes towards the western sky, and then some stars come up, right? And then you have Orion and the moon also rising, and then the moon is reaching maximum height. There's a comet over there, and then it's gonna set in the western sky. The day is coming by, the sun is coming, and then we have another day. So this is the first motion I would like you to put your attention on it. It's called daily or diurnal motion. Daily or diurnal motion is the apparent motion of sky objects on an hourly basis. So if you look east, let's do that. Let's look east. if you look east, we see objects rising in the eastern sky, so going from below horizon to above horizon, and then see they are rising. They are going from below horizon, and then they are going overhead, and then eventually they will all set in the western sky. Western sky, right there. Orion is setting, Pleiades is right there setting, Taurus is setting, and the moon is gonna set too. See that? And another day is coming. Now the day goes faster because we are in the winter time, so it's all understood. And now we are already in New Year's, January 1st, 2016. So what is the cause of this daily or diurnal motion? Let me put a halt here and go there. And let's go to our point. So can I do annotation? I think I can. File, edit. Back to document. Edit. Is that how I do? Okay, so Earth, he is Earth. The sun is over here, right? The sun is there. He is Earth. So Earth goes around the sun, called this revolution. I will talk about it in a little bit. But Earth also rotates around its axis of rotation and takes about 24 hours for that to happen. So which means that sometimes if you happen, so here I'm drawing you with a big sombrero right there, see that? So if you are standing on an hemisphere that happen to be facing the sun, we call that daytime. But see, 12 hours about 12 hours later, you and your big sombrero is going to be on the dark side of Earth, on Earth shadows. And then we experience nighttime. So Earth rotates on its axis of rotation, and because of that, we experience days and night. And basically, this is what we are observing here, right? Because Earth rotates on its axis of rotation. The sun, the moon, and the stars in the far back, we see them apparently moving in the sky from east to west because we in the space rotate from western sky to the eastern sky on an hourly basis. So and so this motion is not at all the stars that happen to be kind of a glue in some imaginary celestial sphere. So it's not the stars that happen to be going around us. We rotate on our axis of rotation. And as a result of that motion, we perceive the stars going on uh, this motion. Okay, so daily or diurnal motion caused by Earth rotating on its axis of rotation. Okay, so let's go back to our PowerPoint. So we have this question here, right? Go back there. The sun rises in the east and sets in the west. Which way is Earth rotating? So rotates from west to east. So it rotates towards east. This should be the right one. Okay, so if you have the sun casting light like that, here's the sun. So Earth is somewhere here. This is the North Pole. Earth rotates this way. And so, for instance, if you happen to be here with a big sombrero, you're going to see the sun rising, right? And then 12 hours later, you're going to be dragged to this position in the sky with your big sombrero. And then you have to look west to see this is west. We have to look west to see the sun setting. Why the sun sets? Because a few minutes later or hours later, you're going to be here and Earth is going to be in the way. If you look west, you're not going to see the sun. So if you look towards east, that's the direction in which Earth rotates. You see more and more stars, different stars rising, and eventually when you are here 6 a.m., you might be able to see the sun rising again. It's another day coming by, right? So Earth rotating on its axis of rotation. So in ancient times, they didn't have telescopes, they didn't know astronomy as much as we do today. And Greek philosophers, they conceived this notion of celestial sphere. It's not a real sphere. I mean, this celestial sphere doesn't exist, but it's easier, and we still use this concept of a celestial sphere as a way to position stars. So no matter what you see in the sky, you can always project what you see in a background, and then you can imagine this background to be made of a kind of a sphere, but it doesn't exist. But it helps to position things, and if that is done, you have this notion of celestial sphere, something that really doesn't exist. And so, if you extend Earth equator onto infinity, you define what's called the celestial equator. And if you extend Earth's axis of rotation onto the celestial sphere, you might define the north celestial pole and the south celestial pole. And if you look towards Polaris, which is a star very much close to the north celestial pole, let's do that. So let's now look north. So if you look north, there you go. See north. So if you look north, what you perceive is that, let me get rid of daylight, wait a second. Hide daylight, there you go. What we perceive is all stars, they seem to be rotating or going about this little fellow here. See that one? This is Polaris, the northern star. So Polaris is not a bright star at all. Polaris is a star that belongs to an asterism named the Little Dipper. The Little Dipper. And it's right here. See, 1, 2, 3, 4, and then you have a Dipper right there. So Polaris is pretty much close to the north celestial pole. If you take a line and you draw that line perpendicular to the floor, you're going to find your true north within 1 degree. So it's very nice if you can locate Polaris in the sky. In fact, you can use the Big Dipper. See if the Big Dipper is right here. See the Big Dipper? 1, 2, 3, 4 is next to a comet. And the handle of the Big Dipper, you take these 2 stars right here of the Big Dipper, and then let me stop this rotation. So you take, oops, it didn't stop there. So you take these 2 stars and then you connect them. That will take you to Polaris. It's about 30, almost 40 degrees. Let me see if I can do that. There you go. It's right there. So it's about 30 degrees from one of the pointers. 30 degrees if you make a fist at arm's length. So your fist projects in the sky 10 degrees. So from the pointer star to Polaris is about 3 fists, 3 times 10 degrees. And then you can locate that. So if you are a Girl Scout or Boy Scout, you learn all this stuff. Okay, so let's go back to our PowerPoint. It's right there. So we are talking about these basic motions that we are subject to. Now, second basic motion. The second basic motion is Earth revolution around the sun. So this is a different ball game. So we have the sun in the center or at the center of our solar system, and and all planets go about in the same direction. See that? The same direction. So if you are standing north and then looking down the solar system, you see all these planets going around the sun in a counterclockwise direction if you are standing north. Counterclockwise. Counterclockwise. Counterclockwise direction. So why is that? Well, that is we are going to learn in few days. In fact, when we start star formation, we learned that stars like the sun are formed out of gas that exists in a galaxy, and this gas happen to be contract under its own weight, and we call that contraction force gravity. So gravity brings the gas to a central location where the star is going to be residing, in the case the sun. But in the process of bringing the gas to the center of mass, the laws of physics are such that nature prefers to, if you have a cell of gas in a certain position with respect to the center of mass, and if the cloud of gas has some initial rotation, so the fall of this gas is not going to be radial. So it's not going to be all falling like a straight line towards the center. So depending on where the gas is with respect to the center or the axis of rotation of the original cloud, the gas might decide to fall on a circumstellar disk, and then from the disk it will fall on the star, more precisely in the stellar equator. And so planets like our Earth and Mercury, Venus, Mars, so on, so on, so on, and the satellites and asteroids, comets, all these objects, they all formed out of this circumstellar disk that happen to be flattened and coinciding with the equator, with the Earth equator, with the plane that passed through Earth equator. So, and then eventually, as this gas cooled down, and then you have all these planets being formed. Okay. So Earth is one of the planets, revolves around the sun, and it takes 1 year, 365 days, and about a quarter, 365 days and about a quarter to complete this revolution. So it's not exactly 366, it's not 365, it's 365 and a quarter. And that's why every 4 years we have to add another day just to make corrections, and it's a complicated issue. The calendrical corrections we need to do in order to have a nice way to understand what's going on. But as a result of Earth's revolution around the sun, there are things we experience in our daily lives. The first one that I would like to call your attention is we see different constellations in the sky as the time and the year goes by. So let me show you again in the Starry 9 software. So look at this. Now, let me bring here one of the lines that we call, how do I do that? So system quick find. You know, I just brought the software and I'm not so smart about it. I can't navigate so easily yet. Let's see here, just a second. I want to bring equator. There we go. And then also bring I think I can get right here. View. there you go. That is Scorpio right here. Scorpio. This is Libra. This is Virgo. And then you have Leo. And then you have this thing. So one thing that I would do now, I will stop. I will stop. Let me label planets, planets and moons. There you go. And what I'm doing is I'm gonna keep this star kind of a fix it. See that? The time's ticking, and when I press this button here, I'm gonna go further. See that? See that? See what's happening? See Jupiter there? See the moon? So the moon is passing through these regions, through this constellation we call the zodiac. And the moon is passing again because it's another month. March 8, March 9, so it's March 10, 11, 12, 13, and then it goes again, right? March 20, and then when it's about April 20, the moon's gonna come again. See that? So if I speed this up, and I will say the sun is coming by this region in October. So in the following year in October, the sun is gonna be visiting that region again. There you go. August, September, October, it hit. So what I'm doing here is Earth is going around the sun. Earth is revolving around the sun. See? But we are this software is enabling us to see this motion as if we were staring at the same sky region all the time. And then we see something interesting, and that is, well, if I keep fixing to a certain sky region all the time and fix certain constellations all the time, for instance, this is Leo. Let me bring labels. No, that's not what I want. Constellation. So if I bring if I keep staring at the same constellations all the time, what I get is this: there are some objects, and we call them planets. See, there are certain objects we call them planets, and the sun and the moon. See, Venus is coming by, that are seen to move with respect to those stars. So they are not stars, they are planets, right? Planets in olden days were called wanderers because that's what they do. They kind of wander in the sky as a result of we Earth going around the sun on a regular basis. So let me stop this motion here now. And let me do something different. So now I'm back to diurnal motion. See that? The time is ticking, few seconds, few minutes every second. So things are going from east to west, as we learned before. But at the same time, Earth is going around the sun. So in July, let's say 7 a.m. No, let's go to p.m. In July at 11 p.m. Stop there. So what do we see in the sky? We see Pisces in the sky at 11 p.m. In fact, 12 a.m., midnight. How about midnight, right? Now, if I go another month, now I'm in August, and thought I wanted midnight. 12 a.m. So I still can see Pisces, but not in the same position. 30 days. So let's go to another month, August 22nd, 12:36 a.m. Go 1 month. Now is September, see Pisces. Now let's go October. See what's happening with Pisces? So same time, every single month that passes by, different constellations are seen in the sky. So that eventually Pisces won't be visible anymore during the night. I mean, we could see during the day, but the sun will not allow us to do that, right? So um, this the fact that we see different constellations during daytime, or on a 24-hour period, indicates that Earth is going around the sun. So this picture here in your book is very nice because it showed this quite well. For instance, in September, August, September, see that? Beginning of September, you can see Capricornio in the sky. But in December, November, December, Earth is going to be in this position, um, or more particularly in December. If you look towards Capricorn, you can't see it. First of all, the sun is in the way, right? It's daytime. You can't see anything besides the sun, perhaps the moon in the sky, but certainly not Capricornians, first of all. But you can see, for instance, Gemini, you can see Taurus, because they will be visible. So the fact that, or as a result of Earth revolving around the sun, enable us to see different constellations during different months of the year. That's the first thing. The second thing that is also a consequence of that is seasons, right? Seasons. So what is the main causes, the main reasons underlying seasons? Well, it's because of this tilt, 23.5 degrees, the tilt of Earth's axis of rotation with respect to the perpendicular to the Earth orbital plane. We call that ecliptic plane. Ecliptic plane. Okay. So this tilt is what it causes the seasons. So sometimes Earth is tilted towards the sun, and then we call that summer time. But you see, at the same time, the northern hemisphere is tilted towards the sun, the southern hemisphere is tilted away from the sun. And then southern hemisphere experience winter time. See that? So your book, and towards the end, there are very nice animations that explains and illustrates quite well um, the seasons. And in when we start our chat rooms, I will run some of these animations. So if you are there, if you are curious, yes, I will explain that to you. In fact, it's right here. Okay. So this is pretty much for chapter 2. Um, oh, phases of the moon. So the moon goes through a cycle of phases because the moon doesn't have proper light. The sun is the one who illuminates the moon. So no matter which position the moon is in its orbit around Earth, the moon is always half lit by the sun. Can you see that? See, the part of the moon to the right is dark, and the part of the moon to the left is exposed to the sun, so it's always bright. But from Earth, we see only a small fraction of that lit hemisphere. So when the moon is here, we see it, just a tiny fraction of it, and we call crescent. When the moon is at this position, we see all the lit hemisphere, and we call that full. And when the moon is here in this position, exactly in the line connecting Earth to the sun, um, then we don't see any of that lit hemisphere, and we call that a new moon. Okay, so the phases are the result of the moon orbital motion around Earth, and the fact that we do not see always the same lit hemisphere all the time. We see fractions of that lit hemisphere, and then we call that perception phases. Okay. Now, when it happens, so that when the moon is in the new phase, it might happen when the moon's orbital plane is such that the moon, Earth, and the sun are in a perfect alignment, and we say that the moon is part of the line of nodes, and the line of nodes is a line that indicates the intersection of the moon orbital plane and Earth orbital plane. So when the moon happened to be a few degrees from this from the nodes, we experience what we call eclipse. When the moon is in the new phase, that eclipse is solar eclipse because the moon is blocking the sun. Now, if the moon happened to be if the moon happened to be on Earth shadow, we call that lunar eclipse. So the moon is being blocked. In fact, the full moon, which is all bright, so the bright hemisphere of the moon is now in complete or in almost complete darkness because it happened to be immersed in Earth's shadows. We still see a little coppery moon as a result of refraction of some of the sun's radiation through Earth's atmosphere, and then we have some red beams of light going towards the moon at that time, and then we see it kind of dark. Okay, and pretty much that's it. I have a question. It's a quiz question. Quiz question. In fact, let me explain. What can you do? What can you do to find out? I mean, at what time of the day a specific moon phase is rising or setting? So the way you solve this, and this I have a quiz question for you. So a quiz question is at. So first of all, you have to know which moon am I drawing here. So this is a full moon, okay? Full moon. This is a full moon. So this is more like a walks in gibbous moon. The red is the bright part. This is a waxing crescent moon, okay? Waxing crescent moon. So if I reverse all of that, it becomes waning. So this is a waning crescent. This is a waning. In fact, last quarter, more like a last quarter. This is a waning gibbous. Waning gibbous. Waning gibbous. Okay. So let's take one of the moon phases. I will invent one here. So this is a quiz, and that will give you extra credit. Okay. So the question is, at what time of the day is this moon? Let me see. Setting. This is a all or nothing sort of a points. Either you got it or you did not get it. Okay. So, and which moon should that be? Okay, let me see one here. Setting. Let me get a tough one. How about this one? How about this one? How about this one? And again, red is lit, right? Red is lit. So first of all, I have to know which moon phase is this. Have to know which moon phase is this. Red is lit, and then the question is, at what time of the day is this moon setting? and then you answer the question, and then after the quiz is closed, I will uh, give it or not the points. But how do you know at what time of the day a moon is setting? So it's a little tricky thing you can do. Let's see if I can open a clear page. Do I have a clear page here? No. I can use this part. So here's how we do. First of all, you have to know from where the light is coming. So you have to put the sun somewhere. And you're looking at from the perspective of North Celestial Pole, which means if this is Earth, this is pretty much 6 p.m. I'm sorry, this is 6 p.m. This is midnight. This is 6 a.m., 6 a.m., and this is noon, right? Noon. Now, let's place now the moon, and you should be able to um, tell which phases those are. So if I place the moon here, the moon is right between Earth and the sun. This is the new moon. This is the first quarter. This is the full moon, and this is the last quarter, right? So waning moons are those that start on the full moon and go all the way to the new moon. And those are waning phases. And waxing phases are those that start in the new phase and go all the way to the full. So those are waxing. So you should be able to draw this, right? So you have to do a couple of times by yourself. If you never have done before, that's the time to start doing. If you don't do it, you can't learn this stuff. So try to do that first, which means place the sun in a given sky position, place your little planet Earth right there with the North Pole in the center, and this line, the circumference, is the equator, sort of. And then you have to put the time. So right underneath the sun is noon, right? This is noon, 6 p.m. because Earth rotates like that. So 6 hours later is going to be 6 p.m. at this position, and then midnight should be here, 6 a.m. should be there, and noon again. Okay, and you should be able to locate the basic moon phases like the new, first quarter, full moon, and last quarter. Now the crescent phases are either here, like waning crescents, or here, waxing crescents. And your gibbous phase should be here, like the waning gibbous, or here, the waxing gibbous. Okay, so you have them all. Now, how do you figure at what time of the day these or any given moon phase is supposed to rise or set? It's very simple. Very simple. Use the T rule. You know the T rule? Let me teach you the T rule. The T rule is coming. It's right here. Okay, place the sun. This is the sun. And then we do that nonsense again. That's Earth, right? And then you have the times. So this is 6 a.m., noon, 6 p.m., midnight. So you have the times, right? The clocks, because you have set the sun at this location. So let's say I give you a moon phase. I mean, any phase. Which moon phase you would like to take? How about a gibbous, waxing gibbous? This is a waxing gibbous. This is the terminator right there. So waxing gibbous. So waxing gibbous, you should know where to place it. So you know all these phases are waxing, right? Those are waning. So waxings are those phases. And waxing gibbous, the moon is somewhere here, right? So once you locate the moon, so you want to find at what time of the day this the waxing gibbous moon rises and sets. So what do? You have to place it here. First you have to draw this, draw that, and then you place the moon in the proper position. What do you do next? A T. What do you mean by that? Well, you just take a line connecting the moon to the center of Earth. Done. And then you make a T. like that. Done. And now you have to figure out what times of the day those interception points are. For instance, this should be what? About 5 p.m., right? And this is what? About 5 a.m. So this moon phase is setting at 5 a.m. and it's rising at 5 p.m. So this is the rising time, this is the setting time. So because you made a T. Simple, huh? Okay, let's try another one. How about last quarter? Last quarter like this. Last quarter. At what time of the day the moon last quarter rises and sets? So you do the same nonsense again. Choo, 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 that's the sun. And then you place Earth right there. And then you have the times. This is 6 a.m., noon, midnight, 6 p.m. Okay, so where do we place this moon? First quarter. Well, you have to know that first quarter goes in here. What do you do next? The T thing. Done. Rising time, setting time. So it rises at noon, sets at midnight. Capiche? Okay, have a nice one.